Thank you, Professor. Good morning, everyone. My presentation will be about investigating microstructural features of granitic rocks and their effect on the mechanical parameters using the grain-based finite discrete element method framework. This work is collaboration with my colleagues Bizawet and Ali. I will start this presentation with an introduction of grain-based modeling capabilities in capturing rock microstructure and explain microfracturing modeling in FDEM. Then I will present two research showcases of implementing grain-based finite discrete element method to simulate cleavage planes during triaxial tests of granites and to investigate the grain size distribution effect on the mechanical parameters and the acoustic emission in granitic rocks. Then I will end my presentation with the conclusions and potential benefits of this study. So why I'm studying granite? Granites constitute many of the geothermal reservoirs around the world. They also comprise fault zones in the basement and gouge along these faults. Also, because of the granite low permeability, it makes them good candidate for underground nuclear waste repositories. This is an example of granitic intrusion and potential geothermal energy resource in Scotland. Another example also for geothermal clay that is composed or part of it composed of granite is the Upper Rhine Graben in Germany and France. So rocks are assembly of minerals bound together by natural processes, and these minerals are formed with the known microscopic crystal structure as shown here in this microscopic image of sandstone granite. Conventional numerical modeling of rocks uses mesh elements to introduce different mineral phases and heterogeneities in the model. However, this simplified distribution of the heterogeneous material ignores mineral grains boundary effect on the mechanical behavior of the synthetic granitic models. Grain-based is generated using the concept of Voronoi tessellations. These Voronoi diagrams are created from points called seeds, and the seeds distributed in the space using Poisson's random point process. And edges of these Voronoi regions are created by bisectoring the distance between any two adjacent seeds, and the intersection of different edges makes the vertices which encloses the Voronoi region. So rupture, nucleation, and propagation is simulated in the finite discrete element method using the principles of nonlinear elastic fracture mechanics by modeling the development of a zone of nonlinear material behavior called fracture process zone. Between any two adjacent finite element mesh, there is 4 noded crack element to simulate rupture propagation. Therefore, there is no prior assumption for crack propagation paths, and any path can be captured within the limitation of grain size, mesh size. In this method, the energy associated with the dynamic fracturing of these cohesive crack elements is composed of fracture energy, frictional dissipation, and additional radiated kinetic energy. This figure shows the constitutive relations used in the finite discrete element method. This is the fracture process zone or mode 1 failure, a constitutive relation, and this is a sleepwalking relation for mode 2 or the shear failure. In a recent work by my colleague Ali Abdelaziz, he showed that the grain-based modeling framework enables explicit modeling of intergranular boundaries between various grains while also taking into account the actual morphology of the grains. Here is his simulation that show gouge formation and fragmentation along a fault in a confined granite sample. This sample is standard state granite, and this shows a consistency with what experimental observation have shown. So by using grain-based finite discrete element work, we brought down anisotropic behavior investigation to the grain level by introducing DFN inside the grain to represent the cleavage and the lamination. Cleavage planes, which represent microscopic anisotropy features, is the existence of one or more planes of weaknesses in the mineral resulting from the weak crystallographic planes bonding. There are some processes affected by the cleavage nature of biotite and feldspar in granitic rocks. For instance, events showed early cracking along cleavage planes in feldspar in the fault zone in Earth's crust, and here crack initiation along cleavage in biotite and plagioclase feldspar during thermal cracking of granitic rocks. And this microscopic image is of stand-state granite from our lab, which shows barrel cracking in the feldspar grains. And the last one shows preferable initiation of cracks along cleavage planes of biotite due to iron oxidation during the weathering of granitic rocks. This is a sample of our modeling of stand-state granite using cleavage plane. And this model is before loading, there is no cracks. And at 40% of the peak strength, intergranular cracks, as seen here, started to occur, and cleavage cracks also with orientation parallel or at low angle to the applied vertical load starts to occur. With the increase of the stress, wider range of angles of these cleavage planes start to fail, and more intergranular cracks start also to appear. And we see here a transgranular crack originating from a cleavage in feldspar that is being arrested at the boundary of a biotite grain with cleavage horizontal or at high angle to the applied vertical stress, and it deviates along the boundary without going through the biotite grain. This was also observed by Lee in granitic rocks, where here the cracks originating from quartz and they stop at the boundary of the biotite grain with horizontal cleavage planes. At the peak and post-peak stress, we see more cleavage planes start to fail and more intergranular cracks, and we observe the initiation of some faulting at high angle to this lamellation. And another thing also, we observe the formation of wing cracks that start vertically parallel to the applied load and accommodate themselves along the weakness planes of the lamellation, then resume their direction in the vertical parallel to the applied load. This is also observed by Lee in granitic rocks, and we see here a wing crack in biotite grain. In the post-peak region, more faulting occurs at high angles to the cleavage planes, as reported earlier also by events in the fault zone in feldspar grains. And back to our biotite grain, it now faults. And this is also documented for granitic rocks by rolling here the cracks propagating from quartz parallel to the loading and faults the biotite grain with horizontal cleavage. Another microstructural features, which is the grain size distribution, was investigated to see its effect on the mechanical parameters of granitic rocks. Experimental results show strength deterioration with grain size increase in different sedimentary, igneous, and metamorphic rocks. For example, Olson documented this behavior for marble. Hagman and Friedman show it for carbonatic rocks. This plot shows peak strength decrease with the grain size for granites, which can be fit by log linear relation. Another correlation, which is linear in this case, was proposed to relate the strength of granite to feldspar and quartz grain size. And they both show like decrease of in the strength with the increase of the grain size. Here is the 3 rock samples with highly varying grain sizes. Distribution were used to calibrate our synthetic models. These samples were taken from the Atomic Energy Canada Underground Research Laboratory by Eric Eberhard. And this table showed the mineralogical composition and the grain size distribution for the different minerals. This plot in the left shows the grain size distribution for the 3 synthetic models. These distributions were generated using a log normal random distribution using a different mean grain diameter and standard deviation. And those on the right are cartoons of those synthetic models used in the study. And as you see, we took into consideration that some feldspar grains are larger than the biotite and quartz in the model. Calibration strategy was to start first with the middle-sized granitic sample and to use the same mechanical parameters for pegmatite and granodiorite to restrict our analysis to the grain size only. Simulation results for the uniaxial compressive strength and elastic modulus values are shown here in this plot, along with the experimental data. The results show a good match with the experimental data. With the decrease of the mean grain diameter from pegmatite to granodiorite, the resulting peak strength of the sample value increases. Actually, FDEM method succeeded to capture this behavior compared to some of the recently published model using the particle-based distinct element method. Grain size of granitic rock has been also found to affect acoustic emission during laboratory uniaxial compression test. Acoustic emission, which is defined as high-frequency transient elastic wave generated by the spontaneous release of the stored strain energy in the medium, and it is triggered as a result of strain localization, grains dislocation, and plastic deformation. As we see here in the acoustic emission recorded by Eberhard for the samples simulated, larger grain size result in higher number and higher amplitude of acoustic events compared to the small grain size, and this is due to the larger weakness planes provided by the samples with larger grain size. Another important aspect of acoustic emission is the mineralogy of rock samples. Fracture energy of the mineral phases should be calibrated properly to reproduce laboratory acoustic emission using numerical models. Seismic energy in FDEM is calculated using the excess kinetic energy of the nodes of the broken cohesive elements, and it depends on the fracture energy values of the both mode 1 and mode 2. Those broken cohesive crack elements are clustered in time and space to give a realistic magnitude that is consistent with the power law frequency magnitude distribution, and this can be considered an analogy to the breakage of individual asperities along the fault in a single large earthquakes. This is an example of the acoustic emission catalog generated from finite discrete element method simulation for one of our synthetic granite sample, where the cumulative and the non-cumulative frequency magnitude distribution is plotted and analyzed by calculating the p-value. P-value, which represent the proportion of small to large acoustic events in the catalog, in the synthetic catalog. It is calculated here using the maximum likelihood method, which is characterized by less sensitivity to the existence of outlier, but it highly depends on the choice of magnitude of completeness of the synthetic catalog, which is calculated using the maximum curvature method, basically the magnitude with the high frequency in the non-cumulative frequency magnitude distribution. And currently we are setting up apparatus to record acoustic emission during the loading of standstill granite to calibrate this FDEM synthetic catalog. So how we can benefit from this study? As we see, modeling cleavage minerals provide better representation of intragranular cracks within the grain bodies, and it also accounts for the anisotropic nature of these grain minerals. By coupling these grain-based models to thermal and hydraulic models, we will be able to capture different thermo-hydro-mechanical processes in geothermal reservoirs, such as hydraulic stimulation of engineered geothermal systems and injection-induced seismicity in the nearby faults. Also, accounting for the anisotropic nature of grains will give an insight to gouge formation and friction evolution along the fault planes in the crust. And also, in parallel, we can implement more sophisticated friction models in FDEM simulations. Also, by gaining from what you have seen in Edward's presentation about calibrating acoustic emission sensors, and what you will see next in my colleague Bezawit's presentation about fracture energy, we can calibrate acoustic emission finite discrete element methods to reproduce acoustic emission measurement in the laboratory. And using earthquake scaling diagram, we can better model earthquakes in Earth's crust and calculate their energy budget. With this, I would like to thank you all for listening, and I would like to thank INSERC, Energy Simulation, Petronas, CMG, Shokor for sponsoring our research in the group. And I would like to thank Geomechanica for providing us a RASO license for FDM simulation. And I'm opening the session for questions.